Okay, let's start our first problem, which is the shortest path problem. I defined what is a path. Now it is evident that we are looking for a path with the smallest length in a graph, and we call it the shortest path problem. Something that you should know about graph problems is that in many applications the network, the graph, physically exists. So the problem is defined on a physical network.
Just go through the pipes.
For example, many transportation problems. Okay, you think of transportation problems, you can think of cities as vertices, and the edges show if there is a path between two cities. Okay, then you can easily construct the transportation network of the United States, and you can define many problems, many graph theoretical problems on this network. Okay. But the point is, the application of graph theory and network models is not limited to physical networks. There are many problems which we can model using networks, using graphs, but the network is not a physical network. The network does not physically exist, but we form it so that we can analyze the problem more easily. Okay. This is one of those problems. So I'm showing you a problem which intuitively is not defined on a graph, but we can easily define it on a graph, and we can present this problem as a graph problem. Then we can use the known algorithm for graph problems to solve this problem. This is the problem, machine replacement example. Suppose that you have bought a car today, okay, for $12,000, and this is the information about. In this table you have the maintenance information and trading price of your car after different years of using the car. For example, you know that in the first year the maintenance of your car, because it's a new car, the maintenance is like $2,000. And if you decide to keep the car for 1 year and then sell it, the selling price of the car after 1 year of use will be $7,000. Obviously, the more that you use the car, the annual maintenance cost increases. So the second year, the annual maintenance cost is $4,000. After the third year, for the third year, it is $5,000, and so on. So we have the maintenance cost for the first 5 years of use, and we also have the trading price. Of course, as the age of the car increases, the trading price decreases. So if you decide to keep the car for 1 year and then you sell it, you can sell it for $7,000. If you keep it for 2 years, you can sell it for $6,000, but after 3 years its worth is $2,000, and so on. And after 5 years it worth nothing. Okay. And every time that you sell the car, you can buy, you sell the car, you can buy a new car for another $12,000. Okay. Now the goal, our objective, is to minimize your cost during the next 5 years. Okay. The idea is that as your car gets old, you probably want to sell it because its maintenance cost is high, and it makes sense for you to buy a new car. Okay, because you always want to have a car, right? So the decision that we want to make is when to sell the car, this car, and buy a new car during the next 5 years, so that the cost incurred by you is minimized. Okay? As I said, it is not obvious that this problem can be cast as a network problem, but we actually can do it. Let me present to you the network formulation of this problem. Okay? So I'm going to construct a graph. Okay? And this graph, we are talking about 5 years scheduling. So I will have a vertex for the beginning of every year. 1, 2, 3, 4, 5, 6. Year 1, this is year 2, 3, year 4, and year 5. So this is the beginning of the first year, beginning of the second year, beginning of the third year, beginning of the sixth year, which is end of the fifth year. Okay? So these are my vertices. Now I want to define my edges. In this graph, I will put an edge from every vertex I to a vertex j, given that I is less than j. Okay, so from 1 to 2, from 1 to 3, from 1 to 4, 5, and 6. From 2 to 3, 4, 5, 6, and so on. So these. Okay, this is my graph. Now let me tell you my logic. Okay, so you know that I already have a car. I just bought a car, so I have a car in here, and every edge from 1 to a vertex j means that I will keep the car from 1 to beginning of year j, then I will sell it at here, okay, and buy a new car. Okay, so every edge from 1 to j means that this car that I already have, I will keep it until j, and then I will sell it. Okay, by this interpretation of the edges, it is obvious to see that every edge is associated with a cost. If I keep the car, if I use the car from the beginning of year 1 to beginning of year j, then there will be a cost of maintaining the car. So I put the cost in here. In that case, every edge is associated with a cost, and technically my decision is what is the cheapest way to go from 1 to 6, right? Because suppose that I solved it and I get a path like this, 3 to 6. If this is the path that is the optimal solution of my problem, since every edge has a cost, it means that the cost that this path from 1 to 6 has is the least among all possible paths from 1 to 6. Okay, so in this graph, if I find the shortest path from 1 to 6, I've actually found the minimum cost plan to maintain a car for 5 years, right? Now, before we can actually solve this problem, we have to calculate these values. So we have to make a correct instance of the shortest path problem, okay? I haven't formally defined the shortest path problem for you, but I just used our intuition about the shortest path in a network to model this machine replacement problem, okay? So again, this is, as I told you, this is a graph from every vertex I to every vertex j such that I is less than j. We will have an edge, and every edge has a cost, and let's see how we calculate the cost. This is the information, the problem, the information that we had, right? So we know that in our graph we will have an edge from 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, which means what if I keep the car for the first year? From 1 to 3 means I keep the car for 2 years, which means I have the car, I keep the car until the beginning of year 3, then I will sell it and buy a new car. Okay, so the decision corresponding to age 1 to 3 will have the cost that I'm going to calculate. Okay, so 1, 3, for example. Since I'm keeping the car for 2 years, I have to pay the maintenance in the first year and the maintenance in the second year, right? Then I will also have to buy a new car, so I will have to pay an extra $12,000. But when I sell the car, okay, I will get some money, and since I kept the car for 2 years, I can sell it for $6,000. So minus 6, this is the money that I will receive. So the summation is 12. So the cost associated with this decision that I keep the car for 2 years and then I sell it and buy a new car represented by age 1 to 3 is $12,000. Okay. Similarly, for every age, I can calculate the corresponding cost, and I can put it on the graph. Okay. Again, intuitively, if this is a transportation network, and I think of if this was a transportation network, and if every number on the edges represented the length of the path of the length of that edge, then this problem is equivalent to what is the shortest path from 1 to 6? What is the path with the minimum length of the corresponding edges, which in this example will translate to the minimum cost of maintaining a machine. As I said, for example, after you solve it, the solution would be something like 1 to 4, then 4 to 6. This will be an optimal solution, for example, and this means that you have to keep the car for 3 years, then you sell it, you buy a new car and keep it for 2 more years. Okay. So with this example, I just wanted to emphasize that the application of network problems is not limited to the problems that are defined on physical networks. There are many other problems that we can model and solve using graph and as graph problems.
Young man, sometimes the right path is not the easiest one.
Now let me formally define the shortest path problem in graph theoretic terminology, and after that I will show you how to solve this problem. Formally speaking, a shortest path problem is defined on a directed and edge-weighted graph. Okay, so it is we can say something like a transportation network. So every vertex, every edge is a directed edge, which tells us how we can, if we can get from this vertex to this vertex directly. So it is directed. There is also a number associated with every edge, which represent, we can think of it as the length of that edge. Okay, so 12, 13, 2, 15. Okay, a network like this. So in this network, I can easily define the path between vertices. For example, in here there is only one path from A to B, and the length of that path, this is the actual path, and the length of that path from A to B is 12 plus 13, 25. Okay. obviously, like the problem before, the path that we are looking for is not unique, so we have to pick a path with a minimum length or minimum cost. The shortest path problem is defined on a directed graph and edge-weighted graph. Those edge weights represent the length, usually, the length of that edge. And the objective is to find the shortest path, which means a path with minimum weight or minimum length, from a given vertex S to every other vertex. Okay? This to every other vertex actually is a consequence of the algorithm that we're going to use. So it is more natural to ask, if I give you a graph, it is a directed graph, and we know the length of the edges. Okay, it is more natural to ask what is the shortest path from S, for example, to T. Okay, so it is more natural to ask what is the shortest path from a vertex S to another vertex T. But as I said, it's a consequence of the algorithm that when we run the algorithm on this graph, it will give us the shortest path from vertex S to every other vertex. Okay, so we don't actually have to specify the ending vertex. We solve the problem using the algorithm that I'm going to present to you, and after we solve it, we will have the shortest path from S to every other vertex. So then we can pick the shortest path from S to a vertex of interest.